Let's take a look at example 5.22. So it says a 2,540 kilogram test rocket is launched vertically from a launch pad. Its fuel of negligible mass provides a thrust force so that the vertical velocity as a function of time is given as this. All right. Where A and B are constants and time is measured from the instant the fuel ignites. At the instant of ignition, the rocket has an upward acceleration of 1.5 meters per second squared. So the acceleration at 0 seconds is 1.5 meters per second squared upward. 1 second later, an upward velocity of 2 meters per second. Okay, so the velocity at 1 second is 2 upward. Part A wants me to determine what the constants A and B are. Part B wants me to know at 4 seconds after the fuel ignition, what is the acceleration of the rocket? Okay, and then C wants to know what is the thrust force, or with what thrust force does the burning fuel exert in order to cause the rocket to accelerate like that? All right, so let's start. So in order to deal with this, if I plug in 1 for my time, I'm going to have both A and B in that equation. So I'm going to have two unknowns. So what I want to do is I want to take the derivative of our velocity function here to get an acceleration function. And so I end up with A plus 2BT. Now I'm going to plug in that A equals 0 situation. So I have 1.5 equals A plus 2B times a time of 0. This allows me to know that A is equal to 1.5, specifically meters per second squared. Okay, so now that I know A, I can use that A value and my velocity equation to find my B value. So I know that 2 is going to equal A, which was my 1.5, times T, which was 1, plus B times 1 squared. And so I should then be able to solve for B. And so B is going to be 2 minus my 1.5. So this will be 0.5. And here, this is going to be meters per second. So like, how am I going to figure out what second it is? So I need meters per second, but I'm multiplying by seconds squared. So this better be seconds cubed on the bottom there. All right, so now that I have those two values, they want me to find what was part B. Find the acceleration at 4 seconds. All right, so I'm going to take my acceleration function. So this was part A, here's part B. I want to evaluate my acceleration function at 4 seconds. So I have 1.5 plus 2 times 0.5 times 4 seconds. So I have 1.5 plus what, 4? So my acceleration at 4 seconds is going to be 5.5 meters per second squared. So the acceleration is increasing as it rises. This is pretty typical for a rocket, mainly because it's losing mass as it goes, because the fuel it's ejecting has mass. So that's pretty typical. Here we're neglecting any change in mass over that first 4 seconds, but part C wants us to know what thrust force does the fuel exert. Okay, so this is a situation where I have an acceleration function and I'm dealing with my forces. So I'm always going to start with a free body diagram. So there is some thrust force pushing up, gravity pulling down, and when I add up those forces in the y direction, it's going to cause my mass to accelerate. I'm going to choose up to be my positive direction. And so I have the thrust force minus mg equals ma. And so my thrust force is equal to mg plus ma. All right. Well, the nice thing for me is I have an equation for my acceleration, and I know what my mass is. So my thrust force is going to be the mass, which was, what was it, 254 times 9.8 plus my acceleration function. My acceleration function being 1.5 plus 2 times 0.5, so just 1 times t. So if I put that all together, so my thrust force is going to be 2540 times add 0.5 on there, I get 11.3 plus t. Now I can find my thrust force at any moment in time. They specifically want my thrust force at what time? At that 4 seconds as well. What thrust force must be exerting on it? Okay, so I plug in my 4 seconds there. So plug in my 4 seconds, I end up with a thrust force of 38,862 newtons. Now, interesting enough, this thrust force in most rocket problems will stay fairly constant. It's the change in the mass here that is going to change that acceleration value. So that thrust force is going to stay the same. And so as this overall weight gets smaller and this mass gets smaller, that acceleration has to increase in order to make that equation still equal the same number. So there's your example.